Good afternoon, everybody. Welcome to Deep Learning for NLP lecture. Oh, this should be 6. So the first typo now. Great. Yeah, slowly but steadily. I hope this is the last one as well on the slides. Anyway, so welcome to the 6th lecture for Deep Learning on NLP. And today we're going to be talking about, sorry, it's too loud. Classification and learning word. Is it too loud or is it okay? Okay, good. Learning word embeddings, because last time we were talking quite a bit about word embeddings and language models. And today, well, what should we learn today? Maybe we want to learn how to solve a problem. And the problem is the following. So I'm going to give you a large corpus of just plain text data. And I think it's really too loud. Just let me, 1, 2. Okay, maybe now better. I give you a large corpus of plain text data. Let's say, I don't know, Newswires or Wikipedia or the internet, okay? And I want to ask you to build a model that will answer such word analogy tasks. So I want to solve, for example, Germany to Berlin is like France to, what should be the answer? Yeah, Paris. Nice, good. It's a sanity check. Okay, so you're here. Welcome to Deep Learning number 6. Or man to king is like woman to a queen, right? So how can you build such a model if I just give you a large corpus of just plain text data in English? Sounds kind of challenging, right? Because you have no labels. You just want to learn something about reasoning and analogy and something about words and their meaning, right? So I can promise you, or even guarantee you, that after this lecture, at the end of this lecture, you should be able to solve this task, and maybe even like the code it, like program it if you really try hard. Yes. Okay. So, but before we jump onto that, so last time we talked about neural language models and word embedding. So just a quick recapitulation, because I thought I'm gonna change a little bit the depiction of the how we kind of draw these diagrams. So they used to be round, but I just changed them a little bit to to the squares or rectangles to be more compact. But still, I mean, this is the neural language model that as we had last time. So we're trying to predict the word that's coming after these 3 words. So the black, dog, and the next word should be barks. And this is what we're trying to predict. This is our gold standard sort of data. And this neural language model kind of has this lookup table for looking up these embeddings here. So what is an embedding? What was that again here? What was here in these E matrix? Anyone remembers what was the embedding? So what is an embedding for a word? Yes?
So for each word, it's a vector with many different values.
It's exactly, for each word, it's just it's an entry in the matrix and a row in the matrix with some dimensionality, which is up to us to specify, and just a real valued kind of representation of the one-hot encoding word. Okay, so and then this neural language model took the context together, so these preceding words as a concatenation, so stack them after one each other, and then here this is what is this again? This is what is this part? It has a name. Maybe it has a name. Anyone remembers what it is, or what do you think it is? Anyone remembers this part? Yes.
Like 2 perceptrons?
Yeah, it's like a multi-layer perceptron or 2-layer perceptron. Exactly. So here, this is the sort of first linear layer. Then there's this nonlinear activation function, which is typically ReLUs or something else. And then there's another linear projection into what? So what is coming out of here? It's again important. What is coming out of here? The projection, because we're trying to predict a word. So what is it coming out of this? Is it a vector? What is the size of the vector? This is the size of the vocabulary, exactly, because we're trying to say which of these X thousand words is the maximum, should be like the max here. This will be our predicted things. Okay, so this is like just a recapitulation from last time. And again, the green nodes are the trainable parameters, which we very fancily denote as theta. So the matrix of embeddings, and here the weights and biases for both layers. And the gray nodes are constants. Okay. Any question to this diagram? Good. So we're gonna simplify a little bit because it's like very clumsy. So we're gonna first turn this lookup into something shorter, and we're gonna call it just V. It's a function which takes a one-hot encoding and produces the embedding. So this is just a lookup function. It's shorter and not so clumsy. Then we also gonna kind of clamp together the linear layers. So remember, I'm coming back now. We have this linear layer, and all these parameters were some of like, you know, independent, well, not independent, but not part of that. So we clamp them together into just one linear layer, like which has trained all parameters W and B. Okay, so it's just more compact representation of the network. So these are two linear layers, and here's still the nonlinear activation in between. Okay, everybody's fine with that. So we're just making it simple and smaller, so it's more compact because we're gonna, yes. Okay, can you read what's on the top? Yeah, we forgot a softmax for actually predicting the distribution over the vocabulary. Yes, that's a great thing. Exactly. So in order to really be a language model that kind of predict the word, after this last linear layer, we want to normalize it into a probability distribution, which we didn't. I mean, this layer doesn't do any probability distribution whatsoever. What comes out of this layer is just a vector of real values. Could be anything. Could be minus infinity to plus infinity all over the place. And we want to kind of softmax to probability distribution, right? So everybody knows what softmax is. I mean, in the meantime, everybody should kind of remember what is a softmax, because it's really, really important, right? Which kind of could be a hint that maybe we'll ask it in the exam as well. Maybe not, you know, but this is a strong signal. You should know softmax, really. Okay, so we have a softmax, and then this is the loss exactly, and we're computing the cross entropy here, kind of. And this gets optimized through stochastic gradient descent. Okay, so this is the neural language model now in its completeness for predicting the distribution of the next word. Any question? Okay, so before we jump into how to train word embeddings and how to solve this analogy task, we need to talk about the dot product. Okay, so this is a quote from the famous movie. We need to talk about Kevin. Everybody knows the movie. It's a very nice movie, by the way. It's a drama from, I don't know, like from the early 2000s. We need to talk about the dot product. And why we need to talk about dot product? Because it has some inherent properties which will be super useful today in this lecture. And we need to really understand what the dot product is doing, right? So what is a dot product? Okay, so let's have a look at the geometry of dot product. If this is just a recapitulation for you, if you know it, that's fine. I mean, you can now take a break, but maybe you will get a new perspective on what dot product is, okay? So we have two vectors, so now let's be in 2 dimensions first. Okay, we have two vectors, v and u. So what is the dot product of these two vectors? How can you compute the dot product? What is a dot product?
Each vector has a element or entry.
Yes. Exactly, we take each. Yes, that's correct. We take each dimension of these vectors, so there's n dimensions, which is 2, and we just multiply each dimension, each element at these dimensions with the other vector. Okay, so we multiply x1 from one vector with x1 of the other, and so on. Okay, this is nice. What is the meaning of that? What are we getting out of it?
I think the most obvious thing is that if they're orthogonal.
Oh, if these vectors are orthogonal, then it will be 0. That's a nice property, actually. That's true. What else can we say about it? Like any like geometric kind of interpretation? It's also projecting one vector to the other. That's correct. We're getting somewhere. That's nice. Any other geometric interpretation of the dot product? It's related to the angle between these two things. Exactly. Because if you make it a triangle and do a little bit of trigonometry and normalization of the vectors, you end up with the geometric definition. Oh, that's not a definition. It's basically geometric computation of this of the dot product, which is cosinus of this theta angle and these two things. Okay, so what is this?
Length of u.
It's a length. It has a special name also.
The norm.
It's the norm. It has even more special name. Which norm? L2 norm or Euclidean norm. Exactly. So this is the length of the vector. So we multiply by length the two vectors and cosinus of this theta. Okay, this is pretty cool, right? So we know the dot product has something to do with the length of the vectors and also with the angle the vectors are taking together. This is nice geometric interpretation. Who said the projection? You were the projection? Okay, exactly. So it's called, it has many names, like one of them is scalar projection, sure, coming. And if you do the little bit of trigonometry here and take the angles and so on, you will find that actually it's projecting one vector and the other, and it's basically a strength of the projection or strength of the association. Okay, so this is really nice. Dot product has many views on that, and they might have a meaning, which is great. Okay, so then we also had let's have a look at dot product of something called a unit vector. Okay, so what is a unit vector? What is a unit vector? Yes. Well, no, I mean, actually the norm is just one. So a norm of a unit vector is one. It can point anywhere it wants, but it has to be length of one. Okay, exactly. And you can inscribe them in the circle of the radius of one. So here u and v are unit vectors because their length is one. How can you compute the length of the vectors? Pythagorean theorem. So basically it's basic trigonometry or basic Pythagorean theorem. So they have unit length. And now let's look at this. So what could be now? Okay, let me see. What could be a dot product of these two vectors? So they're unit vectors. So what is their dot product now? It has something to do with the angle. So the angle is roughly 45 degrees, right? So what could be their dot product? I'll give you a second to think about it because I have coffee today, exceptionally, and it's actually pretty good. So what is the dot product of these two vectors? Yeah, just the cosine of the angle, exactly. That's the point. Because now, since both of them are of length 1, we have just the cosinus of the angle. Okay, this is cool. So now let's have a look at the cosinus. How the cosinus looks like? Okay, it's a very fancy function, which is periodic after 360 degrees or 2 pi. I guess 2 pi, yes, 2 pi. But I just used the degrees here. And now, well, this is roughly 45 degrees. So 45 degrees cosinus is something zero. It's a 1 over square root of 2, I guess. No, square root of 2 over 2, yes. Okay, so this is cool. Now somebody said, well, what if they're orthogonal? So this is correct. Orthogonal vectors, unit vectors, or any orthogonal vectors have a 0 dot product. And now if you look at this, the angle of the cosinus of 90 degrees is, yeah, it's 0. So everything plays out nicely. Okay. What could be like the least similar, or the most different vector from u now? Where should it point? Yes.
Directly in the opposite direction.
Exactly, in the opposite direction. So the vector z now is going in the opposite direction. So we have 180 degrees, and their dot product is -1. Okay, so this is just a recap of trigonometry. Everybody's with me on that? Any questions? Great. Okay, so now unit vectors, fine. But in general, the dot product is unbounded in real values. Which means now we have two vectors, u and v, and their dot product is, yeah, this is larger than 0, right? Why is that so? Because they're pointing in kind of similar direction, and the angle is less than 90 degrees. Okay, so now what if we extend this v vector into something larger? So what is going to happen with the dot product? Let's call it w. How is going to the dot product? How is it going to change? Is it going to be what? It's going to increase. So it's going to be in relation to u times v is going to be smaller, same, bigger? Exactly. Yeah, because I mean we're extended the norm of the vector, so it increases the dot product. So u times v, u dot product v is larger than u times v, right? So when we are extending the product but don't change the angle, it's also changing the dot product. If we just grow the vector into the infinity, we get infinity dot product. That's fine. That's why it's unbounded. Okay, everybody's with me? Okay, cool. So now let's have another vector here, and it's gonna be this one. So how is this? So it's gonna be y. How is y times u behave with respect to all these things? What's going to be the result of the product of y times u? It's gonna be negative, exactly, because we crossed the 90-degree boundary, so it's gonna be on the other side. So it's gonna be smaller than 0. Okay, so we basically change the sign of the dot product. And now if we finish the argument and just exchange here, or sorry, extend here the y into something larger, so z, what's going to be z times u? So obviously follow the pattern, and z times u is gonna be in relation to z times y, it's gonna be even smaller because everything plays out here. Okay, so is it clear like what the dot product is doing? So it depends on the angle, and also it depends on the length of the vectors. And it could be from minus negative to plus negative. And when the vectors kind of are orthogonal, it's going to be 0. And then anything else will be either negative or positive. And it kind of shows the strength of the association of these two vectors. Okay, any questions? Well, I have a question. So we talk about, strength of association, and we're moving one vector. So the vectors are basically dots. I mean, this is an origin, and the vectors are just dots in the space. I mean, you can plot them as these nice arrows, but they're basically dots. How do you measure kind of relation between dots in a space? There's another kind of thing where you can say, well, this is somehow in relation to something else, right? I mean, yes. Exactly. You can just look, how far these points are from each other. So Euclidean metrics, how far are the others? So the question is, how does the product is related to Euclidean distance? Yeah, I mean, if we want be things together, closer, we can use dot product or we can use Euclidean distance. So is there any, what's the relation of Euclidean distance with the dot product? This is a fair question to ask, right? Because now, here we extended the point here, so we change also the Euclidean distance from here to here. So what is the relation here? Well, actually, it's kind of interesting and nice. So Euclidean distance, right? We take one, we subtract two vectors and then complete a L2 norm. So this is the Euclidean distance. Everybody's with me what Euclidean distance is? Very good. So basically for each, it's a Pythagorean theorem, but in many dimensions. Right. So, well, we take the square of the Euclidean distance to make this argument more simple. Hi. And so we take this Euclidean distance and put a square of that, which means we get rid of this very ugly square root. So it goes away, and we just plug here in the definition. Okay, so this is the definition. We have, for each dimension, we just subtract and make a square out of it, which we can also just rewrite into the product of these two things. Yeah, this is just a simple algebraic operation. We're not doing anything fancy here. Okay, so once we get here, we can just multiply these things together. So we multiply this with this, this with this, and so on and so on. We end up with these three terms. Okay, so still this is an algebraic operation, nothing very fancy, because these are just some real numbers. Okay, once we did this, what can we do with the sum? Sum has a very nice property. So we can basically split this into sum of these additions is the addition of the sums. So we can split it into 3 and put a sum at each entry. So we're gonna basically split it into sum of that part, and sum of that part. So it's still another linear operation. And what we end up here with, okay, well, this looks like a definition of a dot product. Oh yeah, this is dot product of u with itself. Okay, nice. This is another dot product of v with itself. And this is two times dot product of u and v. Wow, okay, not bad. And then obviously if we have u and v are are unit vectors, so length 1, then this becomes 1 times 1 and 1 times 1, which we get 2 minus 2 times their dot product. Okay, so there's actually a relationship between Euclidean distance and dot product. Dot product is kind of more, it's more complex because it could be also negative, which tells you something about, well, you need to have the origin. That's the point. I mean, distance of 2 points is independent of whenever you shift the origin of your space, the Euclidean distance won't change. If you shift your origin, then the dot product will change because you're measuring the angle to the origin, right? But having shown this, we know that if we want to minimize the square of the Euclidean distance, it is proportional to maximizing cosine similarity, right? Because the bigger this gets, the smaller this gets. It's nice, right? So if you want to move things more together in space using Euclidean distance, you can try to maximize their dot product. This is an important observation for what comes later on. Okay, so everybody's with me. I'll give you a second to think about it. Yes.
Then we have two vectors because positive dot product.
Mm-hmm.
And we one of them in length.
Mm-hmm.
That means dot product is big, but the Euclidean it's also three.
Yes, that's a good point. But you have to factor out, I mean, in general, if you have unit vectors, then this holds. If you don't have unit vectors, you're changing the length of one of these. Sorry, you're changing the length of one of those terms because you're extending the vector.
But it doesn't say brackets is equivalent for unit vectors. That applies to 374 brackets.
Yeah. Okay. So this is if you have unit vectors, then there's equality, and that's correct. But then you cannot change the length of the vector because it has to be a unit vector.
It doesn't say for any vector.
Yeah, okay. So proportional is like, okay, let's put it like that. Proportional. Yeah. I mean, this is, there's 3 terms here, and if you change one, obviously it will change the rest of the product. That's true, yes. But if you have a unit vectors, there's equality, and then maybe you don't want to change the length of the vectors, but their direction, and that's what matters, basically, the geometry, not the length. Yes, but it's a good point, yeah. Any other question? Okay, so everybody now should kind of have more insight into what the dot product is. So it's kind of strength of the association, has something to do with the angle, with the geometry, and also it's somehow related to the Euclidean distance of these points. So the closer 2 points are, the smaller the dot product is, because the angle is smaller and the Euclidean distance is also smaller. Okay, sorry, the closer they are, the greater their dot product is. Yeah, that's the point, exactly. The far, the more apart from each other, the smaller the product is, even like negative. Okay. Wow, that's it for the product, and we'll use it later on. But now we have to move to actually the word embeddings and how can we get them. So fast forward, let's talk about the distributional hypothesis and why is it important and where does it come from. So if you recall one-hot word encodings, basically where you have a vocabulary of some size, let's say 3000, which is super small, then each word is represented as just almost 3000 zeros, and one is just one position is set to one sort of one item. And the point is that there is no notion of any sort of semantic similarity. So all words are equally similar or dissimilar. What does it mean here in this example? So you have a word nice, which is represented as this one-hot vector, and at some position there is just one, single one. And you have the same for words pleasant and horrible. The point is, all of them are you know, Hamming distance too. So there is no notion like maybe nice is somehow more similar to pleasant, and less similar or dissimilar from horrible, but you have no chance to tell apart because they're all kind of in this highly dimensional space, and the distance between each of two is the same, right? Is it a good thing or a bad thing? Well, it depends, but if you work with natural language processing and you want to maybe classify movies and represent your document as back of words using one-hot encoding, you want to keep some sort of generalization where if you see something in your training data, like a nice movie, you want to be able to say, well, maybe pleasant movie also has the same label. You want to generalize between maybe synonyms. But one-hot encoding doesn't capture any of these synonyms, anything at all. There's just categorical random variables, okay? It's bad. So it's actually bad. We want something better. Maybe we want something where the words in some vector space will be closer to each other if they're somehow similar, right? So this is the idea. And actually it comes from, even from linguistics, from as early as 1930s, 35. And it's called the distributional hypothesis. And this distributional hypothesis states that words are similar if they appear in similar contexts, okay? So, and it makes a lot of sense. So intuitively, when we encounter a sentence with an unknown word, such as the word, okay, I can't pronounce it, vampinyuk, in the following sentence, I'll read you a sentence and you will tell me what vampinyuk is, okay? So what do you think is vampinyuk? Think it for yourself. No, okay, so let's brainstorm. What is a vampinyuk? Okay, interesting product animal. Okay, this is cool. Okay, any other idea? What is a vampinyuk? It sounds like animal, right? Form of what? A tent. Oh, Native American tent. Okay, yes, it sounds like the Indian, so it could be a tent. Okay, good. Any other cool idea what a vampinyuk is? I have no idea. I mean, but it sounds like an animal. Okay, but I'm biased because I knew the answer already. I mean, there's no answer. It's just made up word. Maybe, I don't know. Marco saw a hairy little vampinyuk crouching behind a tree. So, although we have no idea what vampinyuk is, we now know maybe it's some sort of animal. Maybe it's small, it's hairy, like a squirrel, and it's crouching behind a tree. So vampinyuk is something like squirrel, right? Although we never saw the word vampinyuk before. But just looking at the context, you know, how it behaves, what's the purpose of the sentence, what's the semantic kind of content of that, makes us believe, yeah, I know what's vampinyuk. And if I tell you a story about vampinyuks, then you know it's your old friend. So we infer the meaning of the word based on the context in which it occurs. Okay. It's an example. Everybody's using it. I mean, humans just work like that. Any questions to vampinyuk? So this is cool. I mean, so we have a context, and the word in the context is somehow similar to other words in the context. Because if we replace vampinyuk with a squirrel, Marco saw a hairy little squirrel crouching behind a tree. Yeah, this is something we've seen before, maybe in the stories. So you replace squirrel with vampinyuk, and yeah. I mean, in the context, it's something like the squirrel, maybe. Wow. Okay, so maybe we can use it for representing words, right? We can use the context for representing words. How can we do that? How can we use context for representing words? What would be like the most simple solution you would use for representing words in a context? Yes.
For example, take n words left and right.
Take n words left and right. Okay. And then you're on a good way. So then. Anyone else? So this is a great starting point. So we take some context and words left and right. What can we do then? The words is similar, but yeah, but how do you do that? Like distance, we don't have any vectors to begin with. We have just text and vampinyuk here in the middle.
Right. If I add vectors instead of one hot encoding,
yeah, I'm with you. Maybe it's like already advanced. I mean, we need something more simpler. Okay, anyone else? Yes. Oh yes, okay. Yes. You're taking it too advanced. You're taking it to the end of the lecture. Okay, think something even simpler, something very simple. How can we represent a word using its context? We get a context, 2 words left, maybe 2 words on the right.
Maybe extend the dimension of the encoding, and then just put the index of the last word in the
Okay, so you would extend the one-hot encoding into something bigger. I agree with you. I would even extend it to some matrix, like vocabulary, and I would extend to the matrix. Sorry, you were first.
Yeah, maybe the average of the word embedding.
Oh, okay. You can do that as well. That's already super fancy. We will get there. Any other simpler idea?
So we can represent each word based on the context as a vector. So we have a vector of words, and we like put 1 if this word appears in the context.
Yes, exactly. So we create a matrix where we just have here would be the words. Each entry is a word. And here, each column is a context, like maybe 2 words before and 2 words after. So we collect for each word all these different contexts, and then maybe just count how many times this word appeared. So here would be like Vampinyuk. And here would be context hairy little, crouching behind, right? Hairy little, crouching behind. And we would just say, yeah, I saw it once. Okay. And here you would basically construct a word context matrix and just counting the occurrences of the word in the context. Yes.
On relatively, you say this word appeared 10,000 times, and
yes. So this is like the most simplest thing. You just count occurrences. What do you do with the matrix? Do you want it made relative, probabilistic, and so on? It's a matter of research. So the word context matrices, it's actually a long line of research in NLP and distribution semantics. And then here's again the formalization. So each row represents a word from the vocabulary, and each column represents a linguistic context in which the word appears. And then each of these entries quantifies the strength of association between word and the context. So it could be like counts, basically, or could be somehow like weighted counts or something like that. Exactly. So it's counting and estimating from large corpus. Okay. So everybody's with me. Like this is very simple solution to the problem. Like you have a word, and then you represent it as a vector, where each of the entry in the vector is kind of the strength of the association with each of these contexts, right? Yes.
In the space of the context, gigantic, like category times the power of like size of the context.
Exactly. Gigantic is the good word. Very high dimensions is kind of like very decently set. Exactly. Because you will have, if you just do like n-grams, you will have like, so if you just do like previous and next word, and you have vocabulary of 50,000, how many contexts you will have? 50,000 times 50,000. So it's going to be a huge context vector. So this is one problem. So these explicit word vectors are super highly dimensional, could be even millions. So it could be like super gigantic. The second is data sparsity. So some of these entries may be incorrect because we didn't observe enough data points. Because of this, just you would need like super huge corpus to estimate these probabilities, or estimate the counts correctly. So it will be somehow not a good estimate. What can you do with such a high dimensional matrix is something typically has been done before deep learning in NLP. It's a dimensional reduction techniques, such as singular value decomposition, so SVD. Anyone heard of SVD before? Okay, what is SVD?
I don't really remember.
That's fine. Who remembers what is SVD? Oh, sorry. Yeah, you came. Okay, what is SVD? Yeah, something like that.
Which kind of show the variance in the.
Okay, yeah, yes. So I guess it's right. I don't remember exactly what SVD is because it's not used anymore, like, you know, as a mainstream tool. But you decompose one matrix into a product of 3 matrices, and you use some eigenvalues for that in the middle or something like that. It's very complicated linear algebra thing. So we don't tackle that. That's great because we have something better, which is not so that, you know. SVD is actually hard to scale. I mean, it's so the algorithm for SVD, it's I guess the bottleneck is the size of the matrix. So okay, good. So we have something simple, count-based methods, but they are not the best maybe. So maybe you have something better. Well, what was the goal? Okay, so yeah, we're interested in learning representations of words in context. Okay, yeah. So count-based matrices. What else? Well, we had something for learning representation of words in a context, right? We had it already. What was that? We learned representation of words in a context. Using what? And
predict the context or the next.
The language models in neural networks, exactly. We had language models in neural networks that kind of took a context, predicting the next word, and through that learn the embedding representation. Yeah, we have it already. We have another way of learning word representation of words based on their context. Okay, this is what we did. So we learned something here, and we also learned something in this matrix. So we learned something about words in their context. Can we utilize it for learning some of these so-called embeddings? So embeddings matrix here. So we can definitely use neural language models for learning word embeddings. We can do that, but there's there's a price we have to pay for that, and maybe there's better ways of learning these embeddings. Okay, the interesting thing. So what is remember now our counting base, like 2 words left, 2 words right. What we are having here in this language model. We only have like on the left-hand side. So yeah, why? Well, because we said like language model is from left to right, and we have this Markov property, and we have this count-based language model, blah, blah, blah. But if we want to learn like the embedding, so maybe it's, you know, maybe we don't use that. Yeah. We have another thing here, which is kind of complicated, or maybe computationally quite hard. What was that again? If you're doing these language models, neural language model, there is something which costs lots of time to compute. The softmax. Why is it so? The denominator is a summation over 50,000 items. Super costly to compute, but it's fine. Okay, maybe we can solve it somehow. All right, so let's move on. Let's move from narrow language models to training word embeddings. So the goal of the narrow language model was to predict probability distribution over next word conditioned on the previous words. Okay, great. And as a side product, it learned some useful word embeddings. But the point is, what if we don't need the probability distribution, but just we want to learn these word embeddings, right? We just want to learn these. Sorry, I'm coming back. We want to learn this. We don't care about what's predicted here, whether it's probability or not. We don't care. We care about like good representation of words. So okay, what if we don't need this probability? So we can do 2 things, which I already mentioned a little bit. We can just relax our Markov assumption, and we don't have to look in just to the past, but we can maybe look into the future, left and right. Why not? Count-based, you know, count-based techniques did it as well, so we can do it too. Why not? And we can just completely get rid of this normalization in softmax because we aren't interested in probability distribution. Will it make it faster? Yes. Hell yeah. Will it make it better? We will see. Okay, so let's do the simplification. So the first one is we're gonna ditch the Markov property. So we will look into the future. Here, so previously we had like the black dog and the next word was bark, right? Now we say, okay, well, the target word is in the middle. So we're gonna take the context. We can concatenate together as we had before, and then squeeze it through the 2 layers, multiple, blah, 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 blah. and here's still the softmax, and we're gonna predict the middle word. So it's basically the same as we had before in the neural language model, but now we don't model like the third word given the first and the second, but we just model the second given the first and the third. We can do that. We don't care about left, right. We just take the context. Okay. Any questions? Yes. You first, you second.
So am I getting it right? And we're throwing everything away, but not the context, right? So
we're using the context, but we're saying, well, the context doesn't have to be just from left to right.
Yeah, but it's just the context.
Just the context, yeah. I don't think I understood your question.
Okay, yeah.
Okay, you had a question.
But this only takes one word or two words for context. Usually the context is a lot bigger, I guess.
Yeah, that's correct. But my slides are too small to put like more context in there. So obviously you could have more. Here the word and here the word, which go through V, and you concatenate them. And here again, two words, V and concatenate, right?
But what I mean, like using context usually pros for. I would guess would make more words than just predicting the next word.
What do you mean? Like so you want to take context?
Like
and
if you take context, I don't like what to predict the next word, you just take the last X words.
Yes.
For context, you also take the next X word.
Yes.
That came after. So
yes.
You, I would imagine you would need a lot more. Like,
well, if you do it wisely, not. I mean, you can, yeah. So how big the context is here, kind of it. So if I take 1, 2, 3, 4, 5 context words and concatenate them, from this I'm gonna have like a large vector, which is combination of 5 vectors. Yes, that's correct. Maybe that's fine. Maybe there's a better way to do so, better than concatenation, right? But I can say, yeah, let's take the previous 10 words and after 10 words. Theoretically, I can do that. It's like taking in neural language model, taking n previous words and predicting the next word. And you can do that in neural language model because it just grows linearly, not like in the count-based language models. Okay. Any other question? All right, good. So now we're modeling the middle word. This is fine. So nothing substantially changed. Now we want to give up the costly probability distribution. So instead of predicting the probability distribution, we just want to predict some score of the context and the target word. So what could such a score be? Let's say, now forget about predicting probability of the word. You have a target word and you want you have a context and you want to score it somehow. And maybe the score is something which you want to predict, like as a variable. So you want to score word and context. What could be a score? What is it? Something like which scores we would prefer for certain things and which we kind of don't like.
Could you say something like the target word never appears in this context? It should be like a low score probably.
Say again loud. Sorry, maybe it's right.
If you have a target word and like the target word and it never appears in the context.
Oh, if you have a target word that never appears in the context, then it should be low score.
Yes, maybe a higher score.
And if it appears in the context, it should be high score. Yeah, that makes actually a lot of sense. Yeah. So the idea is that we have a word, target word, and if the target word actually appears in the context, it should be kind of okay. So yes, I want this. And if the target word doesn't appear in the context, it should be lower score. It's same with the counts in the count-based metrics. Like there was a 0 for words which don't appear in this context. Okay, yeah, this is exactly what we want to do. So we prefer words in their true context, and we penalize words in their sort of like untrue context. So words that don't appear. How we get this? How we get this? I mean, how we get words in true context and words in untrue context, or they never been there. We're gonna use a very, very nice trick. We're gonna use something called negative sampling. So instead of predicting the probability distribution of the target word, we create an artificial binary task by randomly shuffling the target word. And we're gonna say that for a positive example, so we have a positive example, and this is taken from the corpus, where the word is actually has been spotted in the context. Okay, so for example, D and dog, and the target word was black. So here the word would be black, and here would be the dog. And this would be a positive example. For a negative example, though, we would kind of shuffle the word and change it to something else. And maybe this something never actually appeared in the corpus. So this would be like negative. And we're gonna say, well, this is gonna be of value 1, it's gonna be of value 0. Does it make sense? So we randomly replace the target word, basically, making it as a negative example. Okay? So how do we sample this negative word? Yeah, so we can use we can randomly sample it from the vocabulary. But maybe you want to kind of follow the distribution of words in the vocabulary. So we're gonna estimate a probability distribution by just counting and dividing. So corpus-based frequency or some reweighting. This is not really important, but obviously you want to maybe sample words that are more common than words that are just super awkward and just appears, you know, with super low probability. But basically randomly sampling, resample the target word. So I have 2 examples of that. Maybe it will be even clearer afterwards. So here's our network, and this is the positive example, and we had it before, so this is cool. So we have the black dog, and the black is the target word. And what we're gonna do now, so you know, okay, so the label is 1, right? Because this is the true example. It's like the positive one. It happened. So, and we're using this architecture as we had before. This is the neural language model kind of change into predicting the, you know, the middle word. So we're gonna somehow model the context. So before that it was concatenation. Maybe it will be something else. We're gonna somehow combine it with the target word because we need to plug it together. And then there will be some hidden layers as before, and we put it through. Oh, now we put it through sigmoid. And yeah, why is the sigmoid here? Okay. Because this is a binary classification, right? We're saying it's either y is in 0 or 1. So we squeeze everything through sigmoid. So there will, from this hidden layers comes a single real value, and we squeeze it through sigmoid. And obviously in sigmoid, if this real value is positive, then the sigmoid will be, the output of the sigmoid will be larger than 0.5. Everybody's with me on that? Okay, so if this is coming positive, and we have the sigmoid, oops, sorry, no, wrong, sigmoid. So something like that. So if this is positive, then the sigmoid will be over 0.5. Okay, good. So this is the positive example. Any questions? Yes.
If I get a value of, for example, 0.5, which means I'm not sure which it is, how do I then?
Yeah, most likely you won't get 0.5. Most likely.
Something above, like 0.6.
Yeah, then you say it's positive. Yeah, it's like binary.
The sigmoid value into a binary.
Exactly. You convert the sigmoid output into the binary. I mean, you use the sigmoid for on the cross entropy loss, basically, because it gives you information how much uncertain the model is. And if it's a true example, you want to be as close to 1 as possible. If it's negative, as close to 0 as possible. So typically the output, the prediction will be somehow like 90 something and or 0 something. Yeah. Any questions? Any other question? Yeah.
Just learning the embedding for the word black and kind of freeze the embedding for the word.
No, I'm learning all of them. I'm learning embeddings for all of them, of all of these words.
So like, but why is the black treated differently than the and all when all embeddings are together?
Why are they treated? Okay, because I'm creating. Why are they treated differently? I mean, they have different function in the model. I mean, this is the and dog is just the context. I wanna have a context, and this is the true kind of the true label. Sorry, the true label, like true word. And I wanna combine them somehow to make sure that if this context and the true label comes together, it comes with 1 here. Because I mean, you can combine, and there's a lot of freedom how to combine these 2 together, right? But if you just cram them into 1 vector, maybe it won't learn that well, I guess. So we have to this thing will be crucial, as we'll see later. Okay, you have a question.
Point to create a task where you can evaluate it and see if the contexts are good.
Yeah.
And make it as simple as possible. And,
Yes.
Why should we explain the other embeddings from the context? If we can just learn them, like, for example, in this context, we look at this good and dog, because due to the fact that there are like neighbors of like, we also get some extra information.
Exactly. Yes. Yes. You're learning for all of the words from the context at the same time. So it's like it's extra bonus because you have the framework to do so, because everything will be web propagated, and you get here the gradient of L with respect to E, and here the gradient of L with respect to E, and here as well. So you just use it as in one pass. You learn more parameters just by one pass for the target word and for other words. Okay, because in the neural language model, you have the same thing. You're learning the embeddings. Let me come back here. You're learning the embeddings here for all of the words of the preceding words at the same time. Yeah, you do the same thing. So coming back to the example, so this was a positive example, and how the negative example, it will be the very same architecture or the very same thing, but here I replaced the word, what was it, black, with some randomly sampled word, which is with, and the label is 0. Obviously, the with dog, you won't see that at all, so it's random word, somehow makes no sense, and the model should recognize, oh, in this context, this word, like linguistically makes no sense, but maybe it could be another word. It could be. So actually, I was thinking like, which word should I put in there, and I had no idea like what could be a random word. So what could be a random word that doesn't have to do anything with the and dog? I don't know, like lecture. Okay, good, maybe lecture. Nothing to do with dog or anything alike. Yes. What Wompanyuk? Yeah, I don't know. So. Wompanyuk and dog could be like cat and dogs, you never know. So lectured, okay, no, lectured dog also makes sense. So it's really hard to come up with an example which kind of don't make no sense. Anyway, so there is a word which is obviously wrong, and the network is trying to punish the network for predicting is correct. So it's trying to learn that this is not the right word. Yes.
What happens with words like the or a, which can appear pretty much anywhere?
They will learn some word embeddings that will put them somewhere like somewhere in the space, which I don't know. It's a good question. Let's try it. Let's train it, and let's have a look at the word embeddings of these A and D and so on, where they live. Maybe they live somewhere. So it's a question. Maybe they will have some syntactic properties, and they will be together because of syntax. Maybe. It really depends on the algorithm, on the size of the context, what is in the context, and maybe the algorithm which is trained on. They will have some embeddings. You can also use embeddings for out of vocabulary words as well, and you typically put it to zeros. Okay, another question? Yes. No. I didn't understand the question. Sorry, say again.
Like how well are they to generalize all of the problems?
What do you mean by generalize?
So they just learn the corpus, so they just learn the word, like the context of the corpus.
Mm-hmm.
So there are different contexts of the word. So can they generalize?
Well, they can, yeah. So whether if you train it on one corpus, whether they will be similar in the other corpus, like generalized to other corpus, or yes and no. I mean, the idea, I'll get you. The idea is you learn these embeddings on some super large corpus, so you see like pretty much everything in the language, which gives you a strong signal already to learn good embeddings, and then you can use the embeddings later on to adapt to whatever you're doing in your downstream tasks, so to say. So they have some, they call pre-trained embeddings because you pre-train, but you can then fine-tune them, so to say, and on your task as well. But the idea is they have some sort of good representation. We'll come to that in the shortcomings at the end of the lecture, okay? You had a question or a comment? Good. Yes, yeah, you have to train it on billions of tokens, like a very super large corpus, yes.
How do the embeddings deal with like negation and stuff, because it's like dependent on the context, like the negation is far enough away?
Yeah, they don't. It's just, there's so many things that, like you can, well, the thing is, you can actually train like syntactic embeddings. If you have your data syntax parsed before, so you treat the context from the syntax tree, you can do complicated stuff if you want. This is like the basic one. You don't need any pre-training at all. You just tokenize the text and have a vocabulary. So there's many things, but there's some embeddings can do some sort of like compositionality. So if you do like negation and the next word and sum them up, they will do something very fancy. Okay. So this negative sampling, everybody's fine with that. We treat it as so we turn our task of predicting probability distribution of the missing word into saying, well, this word was here or this word wasn't here at all. Binary, 0, 1. Easy. It's like a fake task. But it's just great for learning these embeddings because we don't care about probabilities. We just care about these embeddings. They should learn some meaningful representation. Yes?
Generally speaking, for each context, I guess there are much more negative examples than positive examples.
Exactly.
That's problematic because
Sorry, say again, how was it? Like for each context, there are more negative examples than positive examples? Why should be the why? It doesn't have to be the case. It's your decision because you're sampling the data by yourself. You're taking a true context, and there's a middle word, which is a target word. And if you don't do anything, you only have the positive example. In order to turn it into negative example, you say, I'm changing the middle word into something else. And that's how you create your negative example. So your data set could be super balanced. You can have the same number of positive, the same number of negative examples.
then I guess any of the potential negative examples won't learn that they are different from the context, so that they don't belong to the context.
So that's why you typically actually generate more negative examples than positive examples. Yeah, we'll come to that. Okay. Can we move on? Great. So we're moving to one of the famous algorithms for training word embedding, which is called Word2Vec. So it's a bunch of algorithms and also a software package. It's just, by the way, it's written in C and it's just one file of C code. And if you look into that, you would be wondering like how much they cram into one one file of C code to train all these fancy stuff. It was done by Tomáš Mikolov in 2013 at Google, and then he moved to Facebook later on, and so he kicked off like this deep learning, a little bit helped the deep learning wave, NLP. So the code is there. You can have a look in word2vec.c, and you'll be surprised. Python is bad, but C code is even worse. It's really, I mean, they made it for speed, right? So it's really optimized for speed, not for readability. Anyway, so Word2Vec. Word2Vec simplifies the neural language model. So this is our neural language model by removing the hidden layer. So we just completely ditch this thing. We don't care about hidden layers, which means it's actually turning into local linear model because we have a sigmoid and here is some features coming in. So here, this is coming a real value and we turn it through sigmoid and just predict. Yeah. Why is it so? For speed. They just turn out like empirically, you don't need the whole hidden layers and stuff like that for this particular use case for learning these embeddings. Okay, cool. So it's much faster. Now the question is, how the heck are we modeling the context here? So we have words before and words after through embeddings. How can we model the context? What can we do about it? Any ideas? Yes.
Sorry, I didn't understand where we can throw away the paper.
Why can you throw it away? Yeah, why not? I mean, here you're combining the context and the target word into something and then projecting it through something else, like some hidden layers and so on. So you're doing like a multi-layer perceptron, which gives you more, let's say, like expressivity in functions you can model. Yeah, but it's like your design choice. And it costs something, like it costs compute because you need to train the parameters here and so on. Right? We were here, so let me just come back here. So you have this two hidden layers, so you have to learn the weights and parameters and what's the size of these layers and so on. But maybe you don't need that, and that's the case of this Word2Vec. So they just basically after a combination just go through directly to the sigmoid to save compute, less parameters, much faster. Turn out that you don't need it.
Don't you need non-linearity also modeling the context?
Well, the only nonlinearity is, well, you don't need a nonlinearity. I mean, the projection now is, yeah, that's a good question. So all these projections are somehow linear, are they? I guess so. Yeah. That's interesting, right? You don't need a nonlinearity here. I'll think about it. I'll think about it. Why? What is happening here? Because there is no nonlinear operation here, so it should be some linear projection of the words. Yeah, makes sense. Okay. Where were we? Yes, you asked us a question. Any other question to this? Like we just completely make it more simple model. Okay, good. Yes. How can we model the context? Exactly. How can we model the context of these two words? So we have this word here and this word here. So what should we plug here? How can we model the context? The most easiest solution. Exactly. Just sum them. What did you propose? Oh, sorry. No, this is not a one hot. This is embedding vector, which is dim embedding. This is one hot and this is lookup, so it's taking the vector from here and producing a vector. But you can just sum them up. Why not? So we're gonna take each of those neighboring vectors and just sum them up here. We can do average, but it's maybe too complicated. Just sum them up. Why not? Okay, so this is how you model your context here. And now, okay, any questions? Why summing up the context? I mean, we've seen it before, right? Do you remember the average back of words we had? Like you take all the tokens in your document as vectors, could be one-hot vectors, and you just sum them up and do the average of that vector. Lecture 1 or 2 or 3. Okay, so you just sum up the vectors. If the dimensionality of that is, let's say, I don't know, 300, this will be also 300, obviously. We just sum these vectors together, okay? And it's called continuous back of words. Yeah, I think we had it already. The question is, okay, so we have a context modeled as one vector, and we have the target word also modeled as a vector, which is this is dimensionality size of vocabulary times 300 maybe. Okay, does that make sense? Great. So how can we combine the context and the target word? What will be here? Somehow combined. So it's abstract. I mean, I put it like abstract. I give you a second to think about it. How can we combine these two vectors? And think about like what they're doing actually, because we have the true context and we have the false context. So how can we combine these two vectors together? I'll let the gentleman like in the back first. Yeah. We can concatenate them. Okay, fair enough. We can concatenate them. So, oops, where I am. We can concat. Fair enough. Any idea? You were 10 seconds. We can take the dot product. Any other idea? Same idea. Anything else we can combine them? We can take the Euclidean distance. So, okay, great. Yes? Like multiply. Multiply as one vector to the other and get a matrix. Yeah, we're kind of screwed because here we need a real number. Yeah, sorry. Well, actually, okay, so this is the point. Concatenation is a nice idea, but here we need a real number, so sorry, that won't fly. For that, we would need like this multi-layer perceptron in between to squeeze it into one dimension. So it won't work. So here we had the dot product and Euclidean distance. Okay, good. So they both, I kind of produce real number out of them. So a scalar, this is great. What we learned also before, what's the dot product and Euclidean distance? Okay, they have something in, they are somehow related. Not the same thing, but related. What is cheaper? Euclidean distance or dot product? What is cheaper? Why?
Because you don't need square.
Exactly. You don't need to square, you know, you don't need a square root, you don't need to sum all these squares, you don't blah, 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 blah. What is the dot product? One times the other. So you can even like make it parallelizable. Yes. You can vectorize that, exactly. So if you run like large vectors on GPU, you can parallelize even dot product and whatever. So dot product is great. It's just multiplication and summation. You can parallelize it easily. Awesome. So it's gonna be dot product. Because Euclidean distance is also something like dot product as we saw before. So maybe dot product is great. Yes, okay, good. Well, we have dot product. That's a great idea to combine these two vectors. So we're taking the context here, which is the summation of the context vectors, and here's the target vector. So I'll flip that, right? I mean, here I have this in the middle, and here I put the target word on the bottom, just to make it clear. So we have the context. This is the C vector. We have the target word, which is the W vector. I mean, these are not like weights in the linear layer, right? This is like just saying this is the embedding of the target word. And we just make a dot product and squash it through sigmoid and then say, well, if this is 1, this is the true context. If this is 0, this is the false context. So the context words are just one-hot encodings, and they are pushed through this lookup embedding layer. So the only so this is the final thing. This is the continuous back of words word to back. This is the thing you can implement in one afternoon in normal programming language or in 2 weeks in C++. I don't know, or depending on your choice, whatever. This is the thing. The only learnable parameters are just the embeddings. This is the only thing you learn. Everything. Yes, you have a question.
Yeah. Sorry for getting back, but
no worries. Yeah.
E, so the arrows from E to the vectors. So what exactly happens there? E is just a matrix. Right?
E is a matrix. Yes.
You just took the row from.
Yes. Like you mean the V? What is V?
Yeah, that's the arrow.
That's a lookup. Yes.
The row from.
Yes. So V is the C times E, right? The E matrix, which means that the embeddings matrix is, this is a size V, and this is 300 or something, and you say, well, this is one hot, so 0, 0, 0, 1, 0, 0, and you say, oh, okay, 0, 0, 1. This is my row. Exactly. Okay. Yes.
We are measuring the similarity between the context and the target word. But that makes sense here because obviously they are not going to be similar even though they are in the same context.
That's a question. What is this dot product doing? Right? What is it doing? It's doing some sort of similarity because you want the vector of the target word to be more similar to the true context than sorry, you have a context. Okay, so started the context. This is a vector. It's going to be a longer vector than the standard vectors because we are just summing up all these context vectors. We're not taking the average here. We just have a sum. So if you sum up sum up several vectors, you end up with a longer vector. Doesn't matter. Yes, it's weird.
The context by having like a positive and a negative context. Basically having a vector that points in one direction and a vector in a different, the opposite direction, and you sum them up and the context eliminates.
Could be. I mean, I'm recording now, so I won't tell it. But if I design like the word to back, I would say, let's take the average. Not just the sum, but the average. So the average of embeddings could be somehow like the centroid of their meaning, and would be the context. But the sum somehow works better. Maybe it's faster. Maybe it will be the same with the average. I don't know.
But when you sum, isn't it possible also that, for example, different contexts get to the same sum? And
yes, but it's very unlikely. Yes, I mean you can get to the same space with different contexts to the same point, but it's very unlikely because you're in 300 dimensions plus. So the dimensional is really huge, to be honest. So the space is kind of very weird. So you have the context vector, but let's think in 3 dimensions because I can only think in 3 dimensions. So let's have the context vector, And then you're saying, oh, in this context vector, I want to push the true words closer to this vector and kind of push the negative words on the other hand, like pointing in the other direction. Okay? And this is what the dot product is doing. The dot product is positive. Yes, I'm trying to maximize the dot product. Exactly. I'm trying to maximize this thing for the true context and minimize for the negative context. So basically, I have this vector of the context. I want my true word pointing more in this direction. So minimizing this angle, maximizing the dot product in the true context, and pushing the false word, the negative word, in the opposite direction. This is what it's trying to learn. So kind of, you know, making this embedding space behave in a way that it learns these properties. Okay.
And when I want to do the gradient descent or something, do I take all of that and derive it towards the rows of U that I use?
Yes. You do the, you know, the propagation here works always the same. So you compute for each, this is different, each of the blue ones is differential function, which means you have the derivatives with respect to their parameters. And then for updating the E, you need these, what is that? The chain rule for multiple parents. So you sub them up together and get the gradient as well. Yes. So this is just very, I think this is the nice example why we should understand everything as computational graph. Like deep learning is just computational graph, and on each of the node you have the gradient. So if you understand of backpropagation on any computational graph, this is the same thing as we had before. Like there's no difference. You just, each function has the derivatives with respect to their kind of children, or the, you know, the where it comes from, arguments, and there's no other magic in here. Okay. So this is central. Like this is why the dot product is actually working here. I mean, we could try to do the Euclidean distance, but the Euclidean distance is only positive. So it wouldn't really push far away, you know, the negative thing. The negative thing is basically saying, well, the vector should be completely somewhere else, like the different direction. So the word-to-vec is learning useful embeddings, and it's trying to distinguish good word context pairs from the bad ones. So we create a set of the correct context pairs from the corpus, we take it somewhere, and the set here, the bar D of these incorrect word pairs. And exactly, the goal of these algorithms is to estimate the probability. So this is going through sigmoid. The sigmoid, as we know, is estimating probability of the true, something which is true, given the context. And this should be high, or even 1, for the pairs which are from the true context, and low, which is 0, for the pairs from D, right? Because we're squeezing it through the, sorry, let me come back. This will be from minus infinity to plus infinity. Excuse me. So minus infinity to plus infinity. This would be the output, but after here, it's coming just between 0 and 1. Right, so we're squeezing this negative and positive into 0 and 1. Okay, to make it trainable as a standard binary task. So the network scores 1 for the true and 0 for the negative ones. And the, yes.
Quick side of the question. When you have something like the black dog, as you said before, and you have the black dog a lot in the data set, you probably want to train this more often. So if it appears more often in the data, does it also train more often, or is it generally like
yeah, okay, so yeah, your question is like if you have multiple same instances in the data, when you sample them, yeah, what happens?
Like you have the brown dog, which is correct, the white dog and the black dog. Like,
yeah,
it's like 80% of it. You probably want the model to, in most cases, predict like the black dog or something like this, right? Or like train it more on the black dog. Or is it just like anything that's fine?
Anything is fine. Anything which is in this context will be taken as the, no, so the context will be D and dog. That's fine. So it's context, and then there's some adjective in between.
So this model doesn't care if you predict like black or white or brown, as long as it's a data.
We are just, yeah, we'll come to that. We're just super open. It's just a ad hoc notion of similarity. We just plug in there and don't care. We just predict everything which is in the context. Yes.
Data context also just needs to be adapted to these specific features for adaptation.
Yeah, exactly. Yeah, good enough. Exactly. How do you evaluate your embeddings are good? That's another question. We'll come to that. Okay. Okay. I think I have to move on because we have something still to finish. Oh. Okay. So the loss, corpus by loss of word to X is, as we said, like this is the formula of loss. You sum for all the instances the losses, which is predicting 1 for correct and 0 for incorrect. So this is a standard thing. You don't have to remember that. The point is, there was one question, like, each correct word context, we sample k negative pairs from the others. So the negative are k times larger than d, right? So somebody asked here, like, how many you were, right? The negative parameter, so the negative things are sampled actually more often because it's a hyperparameter. So it's maybe like 5 or 20. You have like so many more negative examples for the network to learn than the positive ones. So it's a hyperparameter, works better. Okay, so this was the continuous back of words. Now we can even more relax the context. We can make it even simpler, like even super simple. What would we like? More even simplification of the context. So we have a sum of the context vectors and then the dot product, right? Can we do it any more simple? Any ideas? How could we make it even simpler? So we have 2 words before, 2 words after, take their embeddings and make the sum, and then project the target word. Can we make it even simpler, the context? Something even more stupid. Just 1 word, yes. Welcome to Skipgram. This is it. You can even like make it simpler, where we say, each of the context word will be its own instance. So I'm just modeling the dot product between the target word and 1 context word at a time, here, independent of the others. I don't care about the others. So I'm just basically saying, does this 1 single context word occur in the context of the target word? I'm completely disentangling, because before that we kind of like sum them together and go just directly, like jointly, all of them, all the context words. I'm just saying here, yes, each word. Yes, I just sample more instances and just train them, have more data. It's 2 different models, exactly. It's just 2 different models right now. I'm training, basically, if I have context k, I'm training k different models at once. Or not at once, I'm training k different models, 1 after each other. Does it make sense what I'm doing here? So instead of summing all these context words together, I'm just saying, well, for this target word, first let's have a look at the context word I-1. And what is the dot product? And is it from the correct context, yes or no? Okay, let's have a look at word at C, the other one, like afterwards. Yeah, let's the embeddings and project, and is it from correct context or not? And this is 0, 1. You first, you second.
How do you then decide if you use the word in the context? Will you just say we take the average of all the output from the models, or?
No, you just take 1 word, do the forward pass, backpropagation, and update the embeddings, the parameters. Then you take the next instance, forward pass, backpropagation, or you batch it. You do so like a standard mini batch thing. I don't think so, because okay, so let me do one thing. Let's forget about this completely. So this is 1 training instant, 1 kind of training thing. So I take a word, I take the target word, multiply and say this is from, okay, I shouldn't do this. Is this true context or false context? That's it. So I don't see any matrices or concatenation here. There's not such a thing, I'm afraid. But maybe you want to draw something and talk to me later. Okay, cool. Let's do that. No worries. Okay, good. Any other questions to skip, Graham? First.
So, is it true that in word to back the distance to word to the other distance in the sentence matters, and skip frame it doesn't? For the word embedding.
No, well, it matters kind of, but you have like very small context. You have just one word context. You say, okay, I'm target word. I have some words around, and I just pick one, and this is my context for this one single instance training. And I do it for other words, but they're completely independent. I just think I don't care, whether these contexts they belong together or not. I don't care. I'm just taking one word at a time from the context.
Okay, so in word to back we had multiple inputs, right?
Yeah, in this continuous back of words, we have a multiple sum together.
Okay, then it doesn't make a difference where the word stands in the sentence.
No. They're just completely, yes. So it's like back of word. It's a back of word kind of switch together. So it doesn't make a distinction whether it's like previous or after. Just a context, like a back. Yes, that's correct. Another question. You had one? No. Yes. It's the same model, but you create different instances and different contexts, so to say. It's skip-gram is part of word2vec, by the way. It's just a different algorithm. I didn't say it clearly, so it's still in word2vec, where you can decide whether you want CBOW, CBOW, or skip-gram. Okay. Any question? So yes.
So I will do something and I came to the conclusion I meant to stack instead of concatenate, and then it's just parallelizing it.
Yes, yeah. Parallelizing, it could be parallelizing, exactly. Because they're independent, so you can parallelize. Okay, so basically, yeah, that's what I'm coming to it. Like you have choosing the context, so we have two different things. This is like continuous back of words. So we take the middle word is the target word, and the end words to each side is the context, and we sum them together. Or the skip-gram is you create basically two distinct tasks, and each is pairing the focus word with a different context word, right? This is just replica code we are talking about. And skip-gram actually are to be, found to be robust and efficient to train. And both of them are part of word2vec algorithms. Any question? Okay, good. So let me just finish quickly. So you can go into subword units because all these things are just on the word level, and if you have like a morphological rich language, you have troubles with your vocabulary and stuff like that. So you can, this is the limitation. Let me skip that because this is clear. But how about we split a word as a back of character engrams? So we go into subwords, and each of these character engrams has their own embeddings, and we represent the word as a sum of engram embeddings. It sounds weird. I'll show you the example. It will show much weirder, but it works in practice for highly morphological languages. So you take a word like eating, and you generate, okay, this is you add two special symbols, one for the beginning and one for the end. And you generate all engrams, character engrams of size 3 to 6. So it's gonna be this, then length 4, length 5, until length 6. So these are all sub character engrams. And each of them will be now in your kind of inventory of words or vocabulary sort of, and each of them will have their own embeddings in the matrix E. And then in order to find the embedding of the word eating, you just sum up together the words, the embeddings of the word, the embeddings of the engram, character engrams constituting the word. Why is it good? Well, because it's learning, if you have like out of vocabulary word, for example, Vampinuk, beautiful, Vampinuk is great. So we have Vampinuk, something like that, and you don't know what is that, but there's this Pinuk, And it maybe, maybe the embeddings on PNUC has been learned on some different contexts, like, the other animal, which is ComPNUC. And it has been seen in your training data, and the INUC is part of learn the embeddings, so it kind of transfers some of part of the words. Yes.
So basically, you can learn information about like endings or
Yes.
or stuff like that.
You can learn much more morphologically or informed embeddings here. So it really works for morphologically rich languages. Finnish, super huge morphology, and Slavic languages, Czech and so on. So this works well. Yeah.
But here, if I have two words like, for example, cool and school, which don't have anything to do with each other, it's gonna get a very
Sure. Yes. Yeah. Sure. But then you still have the cool and school, and then cool. Yeah, there could be maybe. I think so. Okay. Well, you have ch here, but maybe the ool will be a shared thing. Yes, but just a part of that will be shared, and the whole thing, the school, also will be part of that because it's shorter than 6 characters. And maybe these embeddings of the word will be more representative in these. It's trained with SkipRAM as well, so maybe it will learn better embeddings for the whole word, and the subwords will just be part of that. It's hard to tell what's in these embeddings, like 300 dimensions or 600 dimensions. Yeah, that's a fair point. Okay, any questions? Good. So what is good about embeddings and what is bad? I need 3 minutes and I'll finish. Advantages. So how can we use word embeddings? Obviously, each word lives in a space of several hundred dimensions. So we use this as semantic input to any neural network instead of one word encoding. And this is an instance of transfer learning where you pre-train or self-train on an auxiliary task, and once you train them, you plug into more complex model. So we can use them. We will use word embeddings for anything down the road, like the recurrent neural networks and so on. So, for example, we can represent a document as an average of its words embeddings, average back of words for text classification. It mostly will work better than just one hot encoding, depending on the task. Very cool. And this is also like word-to-vec was, why the deep learning revolution in NLP around 2015 took place. So word-to-vec has been like one of the super important contributions to the development of deep learning in NLP. So we can use this for plugging into neural networks. Okay, good. Semantic similarity and short document similarity and query expansion. Okay, so here in this paper, they try to use it for query expansion using word embedding. So if you search for something in a word, then maybe you want to find a synonyms, right? Or something which is similar, because word2vec will learn some synonyms because synonyms live in the same context, so they will have similar embeddings. And they said, like, using word2vec's UVec of words embedding approach applied over the entire corpus on which search is performed, we select terms that are semantically related to the query. Oh, this is cool idea, right? So you have your database of products, your query term, and even though there is not exact match, you will find something which is like embeddings close in this embedding space. Okay. What can go wrong here? Well, so I tried to search, I think Reve kind of applied word embeddings last year or a couple of years back into search. And I tried to buy COVID test. And I typed COVID in there, and it gave me 2 Corona beers, like the thing, because they use some word embeddings trained on whatever news. And these word embeddings learn that COVID and Corona is the same thing. Obviously, Reve had no COVID tests in there, but had beers of Corona beers. So if you type here in COVID, it returns Corona. Yeah. So query expansion with word embeddings might be tricky because it's not like it's word embeddings. If you make a comparison and Euclidean distance or cosine similarity, it's not directional. It's just it's a distance. So yeah, in this case, it failed. I can imagine like, yeah, sure, we have word embeddings, much better for search. I'll put it in there. Yes. Awesome example. Okay. I promised you that you will learn how to mine analogies with word2vec at the beginning of this lecture. So Germany to Berlin is France to Paris. You can take the embedding of Berlin, subtract the embedding of Germany, add the embedding of France, and it will output a vector X, which is closest to Paris in this embedding space. This is cool. This is really cool. So you learn something about properties of things, and you can do this vector arithmetic to find analogies using just word embeddings. Or this queen. So you take the embedding of king, subtract embedding of man, and add the embedding of woman, and what you get is the embedding which is closest to queen. This is pretty cool, actually. This is pretty cool because in order to learn this, you didn't need anything labeled, anything, any notion of anything. It just learn good word representation from looking into the context on huge, collection of examples. Nothing else. Yes.
So that's back to my question. So it isn't able to generalize.
Yes.
Right. So like in the dog example, for example, if I had like example of black and red dog.
Yes.
Now yellow is also
exactly.
For
Exactly. Yeah, it will put the colors somewhere in the space closer to each other, or adjectives, or depending on which context you train on, but it will generalize. And even more than that, it's able to look around. If you're model testing in the embeddings, you can. We had an syntax-based embeddings 2 years back, so you can watch this video. Let me just finish very quickly. Limitations word embeddings. So the similarity is completely operational. So words are similar if used in similar contexts. That's it. We didn't say anything about they should be similar or syntax, semantic, whatever. Words opposite to each other like buy and sell and hot and cold tend to appear in similar contexts. So they can be in the same space in the embeddings, and it's not a good thing. So that's bad. We have biases in the data. So we learn from data. And these data sets reflect human biases in the real world. So word embeddings encode not only stereotypical biases, but also race or gender, simply vertical, reflecting the status quo distribution of gender with respect to carriers or first names. So this is very cool science paper where it shows like embeddings encode these biases. Like if you type nurse, it's closer to women. If you type doctor, it's closer to men. Why? Well, because it's just the bias inherited from the data. Because we talk more about this is how the world unfortunately is so far, and this is encoded in the embeddings as well. So keep that in mind. And the last point is, yes, you have a question.
But you always have, no matter what you do, whatever you train will always learn from the text that it trains from. And
it learns from the text, yes, exactly.
The text and the bias will always be taken no matter what model.
So okay, yeah, this is a great question, and I will leave it to the so we will have a guest lecture at the end of the semester from Thomas Arnold on ethics, and I think he'll talk a lot about biases in the data embeddings. And one last point, which is really important, that we model like each word has one embedding, but we have words which are kind of polysemic. So bank could be a financial institution, or the side of the river, or star could be a shape, a celebrity, or stars in the sky. And if you use a single vector for all firms, this is quite problematic because we cannot disambiguate the senses. So keep that in mind. Recap: word embeddings are cool. Self-supervised training of word embeddings is really a thing. And we use CBOW and skipgram. You have a question, so yes.
I was going to say that, are there solutions for this? I'm sure there are.
You can have a look here. You can do like disambiguation and stuff like that on embeddings. But we will have better models which are transformers. They take it into account the context. All right. Thanks a lot. See you next week.